Okay, so let's take a look at the next page. Looking at our information for our class, we had a total of 30 samples because we had 10 groups in here. Each group did 3 samples, so that gives us a total of 30 samples. You kind of want to think when they talk about number of samples also as your number of trials. How many times did they do whatever experiment was? Like you guys picked beads 30 times amongst all of you. Our sample size would be 14 here. So your sample size in this case would be number of beads picked. And then our total number of beads within the containers was 70. So what we're going to do is we'll quickly kind of put a little dot plot in of our data over there on the side. Doesn't have to be 100% exact. Kind of looks like we have 2 modes here. So if we take a look at this, this is what we refer to as a sampling distribution. And this is what AP Stats guy was talking about in his video. But instead of dots, what did he use? He actually used the little p-hat symbol. So what you have to keep in mind, each one of these dots represents 1 p-hat value, which again was your number of red divided by 14, since we had a sample size of 14. It can also be referred to as 1 sample. So you got to keep that in mind when we're looking at that. That's one of our samples. And within each sample, we picked however many. So how would you describe our distribution up here? Would this be symmetric, skewed right, skewed left? What would it be? Yeah, this one looks a little more skewed right. So what do you think might be the true proportion of red beads in this container? So if we had to estimate what our true p-value was, based off of all of these p-hats, what do you think it would be? Kind of looks like it's a tie between these two, right? So what would be in the middle there approximately? Yeah, like 0.16, 0.17, somewhere in there. So I'm saying approximately, I'm going to say that my true proportion would be 0.16. So why do we think that? That would be because most samples are around that value. So what would make you more confident in that number? It's pretty simple. More samples. The more samples you have, the more confident you can get in that answer, the more accurate that answer is going to be. So you always want to have more samples. So if I told you that my sample had 9 red and 5 not red, what would that seem unusual? Let's first figure out what my p-hat score would be for 9 red out of 14 beads. What would we have? Divide that out for me. 0.64. Would that seem unusual? Yes. Why? No other values were anywhere near there. What if I claim that the percent of red beads in this container was 50%? Would that be accurate? No, why not? Exactly, no, because none of our values are anywhere near 0.5. So then notice the p-hats differ from sample to sample. Again, this is called sampling variability. Sometimes they refer to that as sampling error, but I mean, it's not really meaning that you made a mistake. It's just because each little container of samples that you guys had a different number of beads into it. So there's variability to our data because of that. So let's take a look at this. So we're going to look at first what happens if we increase our number of samples. Remember, that means our number of trials. So here is a simulation of 30 samples, which is kind of similar to ours. That one, it looks a little bit, more symmetric than ours. Ours kind of looked skewed right. But now what I did is I then did a simulation using 100 samples versus our 30 that we used. What's happened between our graphs other than there seems to be more dots? Don't tell me that one. It stayed the same basically. Okay, what if we went down here? Here is 1,000 samples. Kind of stayed the same, but let's look at this again. If we were up here, what would we say our p-value would be approximately? Looking at this one. I'd say it's kind of closer here, between 0.7 and 0.14 based on that chart, that distribution up there, because that's where more of our values are. If we look at the 100 samples, where would we say it's a little closer to? I say it kind of moves a little bit more towards 14 because you got a few more numbers here. It's getting a little bit more even on each side there. So then if we look at our 1,000 samples, what is our approximate p-value? Yeah, 0.14, 0.21. So what happens is the more samples you have, the more accurate your distribution is. So more samples makes it more accurate. Day one in the packet on your desk that I just gave you. So as it says down here, the more samples you do, the more normal your distribution is going to be. So as you notice, it kind of does become more perfectly symmetrical as it moves on, going down from 30 to 100 to 1,000. So the more samples, the more normal your distribution is. Now, if we change the sample size, however, that's a little bit different than changing your number of samples. So we're going to say we're still taking 100 samples, but instead, I'm going to pick 15 beads in each sample, and then 30 beads in each sample, and 60 beads. So this is our 15 beads. That's our 30 beads. That one is our 60 beads. So meaning within each sample, I'm picking more beads than we did in our example. So if we look at our distributions here, what happens to them? By the time I get to my 60, it's a little bit more what? It's a little bit more symmetrical. It's a little bit more accurate looking also. But if we look here, my 15 sample, I'm going from 0 to 0.33. In my 30 sample, I'm also going kind of 0 to 0.33. But are there as many out here on the edges? No, they kind of move in more towards the middle for that one. If we look at our 60 sample, though, they definitely move in a lot more towards the middle. So the bigger your sample size is, the less spread you're going to have. And that's our two big things. More samples, more normal distribution. Bigger the sample size, the less amount of spread you're going to have. So let's take a look at example number 2. We have here in the below simulations, 30 students are selected at random. So that's our sample size. And asked if they are male or female. The proportion female in that sample is calculated, and this is repeated 100 times. So that's our number of samples. So 100 times they went out and they collected 30 people and asked them this question. And then they let them go. And then they collected 30 more people, asked them a question, let them go, picked up 30 more people. They did that 100 times. So if we look at these two distributions, which one do you think is which? Which do you think is the 30 people? And which one do you think is the 60 people? Yes, 60 is the one on the top. Because your spread is smaller than this one. That's the 30-person one. So although it's the same number of samples, so you can't try to count the dots. And I wouldn't try to count the dots. That's just annoying. It's the spread you want to look at. Huh?
On that last page, there was a lot.
But it wasn't supposed to be 60 dots. It was supposed to be 100 dots. And each dot represented a sample of 60. Okay? So what do you think is the actual population proportion of females at this high school? What do we think our p-value is going to be? I would agree. I would say it's about 0.4. But by visual inspection, they want us to write an inequality that describes the plausible values for p. So when they say that, what they're trying to say is it's not going to be exactly 0.4. There could be some error here. So you kind of want to find the majority of your data. So whether you're looking at the 60 sample size or the 30 sample size, the majority of our data is here between 0.3 and 0.5. The majority of our data for that one is between 0.3 and 0.5. Yep, so our inequality here would be 0.3 is less than or equal to p is less than or equal to 0.5. Or we can write it as 0.4 plus or minus 0.3. I'm sorry, plus or minus 0.1, and we refer to that as our margin of error. Because remember, sampling variability gives us a little bit of error in our data. All right. I don't think we're going to have enough time to get to this one. So with this one is a study done to see if students in high school get approximately 8 hours of sleep. So since this is a histogram, the only difference is this bar going up to 2 means that 2 samples showed 65% get 8 hours of sleep. So that's the tough part of interpreting your histograms. So again, since that was 2, so this one right here, this bar here being 6, means that 6 of the samples that were taken showed an average of 55% got 8 hours of sleep. This one says 11 said that 45% get 8 hours of sleep. So it's not their number of hours of sleep, it's what percentage said they got 8 hours of sleep. Because that's what this whole study was for this one. So I think we actually may start with that next time since we're running out of time today.